Welcome to this webinar describing the Signal Recovery Model 9210 Multi-Channel Lock-in Amplifier. My name is Richard Burdett and I have been involved with the product line for many years. I hope that you will find the presentation useful. The Model 9210 is the first new lock-in amplifier in our range since we introduced the Model 7210 in 2013. It is our second multi-channel instrument and complements the earlier Model 7210. In designing the 9210, we started from scratch and developed an instrument based on a new FPGA architecture, which is a more general purpose unit than others in our range, making it suitable for a wider range of applications. In some ways it can be seen like a Swiss Army knife, with its many tools, each of which is optimized for a different job. The 9210 came out of work by two scientists at Stockholm University who had been using a suite of signal generators, lock-in amplifiers and voltmeters for calorimetry experiments. Replicating this setup was too expensive, so they had the idea of creating a single configurable box which would have all the required functions, but which would be at a very competitive price. This and the following slide discusses the issue of data sampling synchronization. When taking data from several different sensors using separate instruments for each sensor, then there is a possibility that there will be a difference between the times at which data is acquired, which in turn leads to a systematic error in the results. One key feature of the 9210 is that because all its DACs, which generate the oscillator outputs, and its ADCs, which digitize the input signals, are run from the same system clock, data points are sampled at the same time, which in turn eliminates systematic errors caused by different instruments sampling at different times. Of course, in many cases it is possible with systems built out of different instruments to use trigger connections between them so that the data is acquired at known sample times, but having all the functions in one box means that this is not necessary. Let's now consider what benefits are available when using a multi-channel lock-in amplifier. Traditional single-channel units like the Signal Recovery Models 7270 and 7230 pictured here essentially allow the measurement of one signal at any one time. For example, in impedance measurements, the instrument's oscillator can be used to drive the experiment, and the input can be used to measure the voltage developed across the sample under test. However, there is no direct way to measure the current flowing through the sample at the same time. It is of course possible to use external or internal input multiplexing to sequentially measure the two signals, but this would require external computer control and means that the readings are not taken simultaneously. The only way to achieve direct simultaneous measurement of two signals representing signal current and voltage is to use two instruments. And although we have sold a number of systems using, for example, two Model 7230s for this application, it clearly becomes very expensive once one needs to measure several samples at the same time, needing two instruments per sample. Of course, using two instruments also means that one needs to carefully consider which one will be the source of excitation and reference, as well as making allowance for interconnecting triggers to ensure sample data values are correlated. A multi-channel lock-in amplifier, especially one with multiple excitation or oscillator outputs, overcomes these difficulties. Now let's have a look in detail at the Model 9210. As can be seen, the chassis, Model 9210-CHS, consists of a 1U high 19-inch rack-mounted case, which is just 140 mm deep. It can of course simply be placed on a bench instead of being rack mounted. The unit has a brushed aluminium finish and weighs just 3 kilograms. On the front panel are 5 pairs of RJ45 8-way connectors and associated LEDs, each pair being connected to a signal processing board. The instrument is modular, so that it can be ordered with between 1 and 5 such boards. There are 3 types of board available, with different input impedances and input voltage noise specifications, allowing the optimum type of input to be selected for each application. The boards carry the model numbers 9210-high, 9210-med and 9210-low. When the unit is fitted with one board, it provides two differential voltage measuring inputs and one excitation or oscillator output, which in turn allows measurement of the excitation current being generated and the two input signals, so effectively 3 measurements in total. As more boards are fitted, the capacity increases to a maximum of 5 outputs and 10 inputs, so that up to 15 signal channel measurements can be made at the same time. Finally, with the cover removed, it can be seen where the signal processing boards are located relative to the front panel. Let's now take a closer look at the pair of RJ45 connectors relating to one of the signal processing boards. We've chosen these for the signal connection since they provide a very compact way of terminating multiple connections using screened twisted pair cables. They allow Cat7 cables of either type to be plugged in with their other ends prepared for direct connection to the experiment. Alternatively, if the system is to be used with cryostats, in which the signal connections need to be made into the vacuum chamber, then Cat7 jumpers can be connected from the Model 9210 to low-cost vacuum-compatible multi-way feed-throughs on the cryostat, which in turn allow vacuum integrity to be maintained. The left-hand connector provides the two differential voltage mode inputs and the oscillator or excitation output. The latter is provided via two connections, one a direct voltage output and the second as a voltage output but with built-in current measurement. The latter is typically used when making impedance measurements on samples. The right-hand connector provides buffered, amplified versions of the two signal inputs, which are equivalent to the signal monitor outputs on our other lock-ins, and two digital connections. The digital input allows application of external reference, allowing the instrument to work in external reference mode, while the digital output can be used to synchronize other instruments to the 9210. LEDs adjacent to the connectors show when the inputs and outputs are active and when overload conditions are occurring. Now let us look at the oscillator or excitation output in more detail. Remember, there is one of these blocks per signal processing board, providing two physical signals. The required waveform, usually sinusoidal but capable of being set to other formats, is generated by the processor writing values to a digital to analog converter or DAC. The resulting signal is filtered by a low-pass filter and the amplitude adjusted via a variable gain stage. After buffering, the signal is applied to the front panel connector. This is the single-ended output. But the same signal is also taken via a circuit which has a return current measuring stage implemented using either a current shunt, which is used for the higher current ranges, or via a transimpedance amplifier, which is used on the more sensitive ranges. The measured signal passes via an anti-aliasing filter to an ADC, which in turn gives a digital representation of the instantaneous excitation current. Let's turn now to the signal inputs, of which there are two per signal processing board. These are differential voltage inputs, so if current measurement is required on those signal channels, then an external current preamplifier, such as the Model 5402, will be needed. The input signals can be either AC or DC coupled and are fed forward to a variable gain amplifier. A relay can be operated here to disconnect the signals and apply a ground to the following stages. This is needed when calibrating out DC offsets in the system. A variable gain amplifier follows, which allows the sensitivity to be adjusted before the signal is filtered by an anti-aliasing low-pass filter and then digitized. In summary, it can be seen that each signal processing board is generating ADC values representing the signal input 1 voltage, the signal input 2 voltage, and the measured oscillator output return current. The system processor within the chassis is also needed to produce the values which are applied to the DACs, which in turn generate the oscillator output signals. These inputs are processed and the outputs are generated by the main instrument processor in the chassis. Turning now to the oscillator or reference generator, this consists of a waveform generator which can output not only the sine waves generated by the oscillator outputs on other lock-in amplifiers, but also square, triangular and pulsed waveforms. In addition, more complex waveforms, such as the sum of two different frequencies, can be generated. The frequency of the waveforms can be fixed, or alternatively locked to an external trigger signal, giving what is essentially an external reference mode of operation. Note, however, that because this uses a simpler digital phase lock loop than the analog ones used in our other lock-in amplifiers, that as the reference frequency increases, the phase noise also increases. Hence, this mode is best used for frequencies up to a few tens of kilohertz, where the noise is smallest. Each signal input uses the lock-in amplifier configuration shown on this slide. The ADC output can be taken directly to the computer as a waveform record, but is also fed to two dual-phase lock-in amplifiers defined as L1 and L2. These in turn are driven by two different reference frequencies, F1 and F2, chosen from the 8 possible frequencies within the instrument. The lock-ins generate the usual X, Y, magnitude and phase outputs. There is also, of course, lock-in detection of the oscillator drive current at the same reference frequencies F1 and F2 for each signal processing board. In conclusion then, a fully equipped Model 9210 has two groups of 15 lock-ins, making a total of 30. Each group runs at a common reference frequency. The two frequencies can be the same but would normally be different. There are 10 signal channel lock-ins per group, and there are 5 oscillator output current lock-ins per group. Given the flexibility of the 9210, it's useful to consider typical measuring possibilities for different configurations. In a full system, these would include 5 oscillator outputs, each one measuring oscillator current at the same frequency, and 10 signal inputs. The inputs would have dual phase detection of each signal. If we extended this to use the second set of demodulators within the units, this would allow 5 oscillator outputs, each measuring the oscillator current, and again at the same frequency, and 10 signal inputs. However, we would have dual phase detection of each signal at both a reference frequency and, for example, at the second harmonic, so a second frequency. Alternatively, if we used a more complex excitation waveform, we could have 5 oscillator outputs, each now at the sum of two frequencies F1 and F2, and 10 signal inputs. Using all the demodulators in the instrument, we could have dual phase detection of each signal at both F1 and F2. In systems using just 2 signal processing boards, the number of channels is of course reduced pro rata, but the system is still very flexible. I mentioned earlier that the 9210 can be used when the oscillator output is not sinusoidal. For example, it can generate ramp waveforms which, when the inputs are set to DC coupled mode, can be digitized and recorded. In some ways, this functionality is similar to that provided by the Solartron Materials Lab system. Additional functionality provided by the 9210 includes combining multi-signal recordings into one instrument, e.g. you can record X, Y, magnitude, phase from one or a multiple sources and samples, plus maybe a DC voltage from a monitoring sensor. You can apply and analyze DC functions, so constant level ramps, on top of AC signals, creating complex signal waveforms, or just simply record that data as a digitizer. You can mix and match the different output types to perform a variety of experiments simultaneously. And you can use FFT analysis features, making simultaneous measurements on several harmonics up to the 32nd. Finally, you can even use the system as a static gate boxcar averager, which I'll explain in the next slide. In a boxcar averager, the input signal is sampled by a gate which occurs a fixed time after the applied input trigger. Signals during the gate period are integrated and contribute to the output. Signals elsewhere are ignored. The technique is suited to recovering narrow signals which have a mark-space ratio substantially less than 50%. When the 9210 is used in this mode, the trigger delay is set by the phase shift control and the gate width is set by the duty cycle control. The resulting integrated signal is averaged over the gate width by the output filters. The 9210 is fitted with a number of computer interfaces, but in most cases it just needs connection to a 1000 base T network, which is also connected to the controlling computer. The chassis also has USB ports to provide for future development. The 9210 comes complete with a copy of the MCL software, which runs on Windows 7 PCs and later. It is a compiled LabVIEW executable, but it doesn't need a copy of LabVIEW to run it. In its Controls tab, it has a Signal Recovery tab showing a subset of the most common instrument controls and displays, and this is suitable for most simple applications. There is also a more advanced property tree structure which gives access to every instrument feature. A LabVIEW driver is also available. I thought it would be useful to run through a simple demo experiment which shows how the 9210 can be used to measure an impedance network. In this, the oscillator output is used to drive a current through the network. The current is measured by the built-in return current measuring circuit. At the same time, the voltage applied to the network is measured using the channel 2 voltage input, and the voltage output by the network is measured using the channel 1 input. This is the schematic of the network, which consists of 2 resistors and a capacitor. It is built on strip board and connected directly to the ends of a cable, which at the other end is fitted with an RJ45B connector. On this connector, pins 7 and 8 are the oscillator output from the 9210, pins 3 and 6 are the V2 input signal, and pins 1 and 2 are the V1 input signal. The impedance of the capacitor is 1 over 2 pi Fc, where F is the frequency in Hertz and C the capacitance in farads. At 1 Hertz and 100 nanofarads, the magnitude of this impedance is 1.6 megaohms. Since this is very much greater than the value of R2, which is 15 kiloohms, then the network acts as a divider of factor 0.5. We can measure this using the MCL software. Start the software and set up the output. First, select the Signal Recovery tab. Next, select the Output controls in the Config/View selector. Then set the frequency to 1 Hz. Set the amplitude to 2 volts RMS. Set the auto range control in the current measurement section. And finally, click the Output Enabled to enable the actual output to appear. The green LED Output Active will light. Now set up the controls for input V2, which will be used to measure the actual voltage at the input to the network. Select the input V2 controls in the Config/View selector. Next, uncheck the AC coupling box. Then uncheck ground. This enables the input. Finally, make sure the auto range box is checked. Finally, we set up the input V1 controls. First, select the input V1 controls from the Config/View selector. Next, uncheck the AC coupling box. Then, uncheck ground, which again enables that input. And finally, verify that the auto range box is checked. Now that the experiment is set up at the 1 Hz frequency, selecting the Input V2 tab shows that we are applying a 1 Hz 1.9971 volt RMS signal to the network. The input impedance is very close to 30 kiloohms, since it's really the sum of two 15 kiloohm resistors. Hence the current should be 1.9971 divided by 30 kiloohms, which is 6.657 times 10 to the minus 5 amps. If we now select the Output tab, we see that the measured current is 6.6839 times 10 to the minus 5 amps, which is only 0.4% different from that which is predicted by theory, and that is well within the 1% component tolerance on the components used to build that test network. Now we can change the frequency to 1 kHz and see the effect on the measurement. On the Config/View Output tab, select the lock-in frequency box and set it to 1000, which is 1 kHz. At 1 kHz, the magnitude of the impedance of the R2 C1 parallel combination has fallen to 1582 ohms. Hence the circuit current is now much greater than it was at 1 Hz. It can be shown that the combined impedance of R1 and R2 in parallel with C1 is now 15,200 ohms. Hence the current will be 1.99637, that's the voltage being measured at the input V2 input, and divided by that 15,200 ohms to give 1.3136 times 10 to the minus 4 amps. The measured current, as shown on the Output tab in the MCL software, is 1.3101 times 10 to the minus 4 amps, which again is well within the range expected due to component value tolerances. The property tree in the MCL software is used to set up more complex options. Here we see it being used to adjust the oscillator output to use waveforms other than sinusoidal. This screen shows the extended controls for the lock-in amplifiers, including harmonic selection and extended filtering. The 9210 can be used to simultaneously measure at multiple harmonics of the reference frequency. For example, in swept experiments, detecting at the fundamental and the 2F is useful, since the 2F signal gives a derivative of the F signal, allowing maxima and minima to be easily identified. Nonlinear effects can be studied and modelled. In 3-ohmega thermal conductivity experiments, measurements can be made simultaneously at F, 2F and 3F. The multi-harmonics mode is accessed via the property tree. Here we see a fully equipped 9210 set up to generate and measure signals on board A at the fundamental frequency F, 1F, on board B at 2F, on board C at 3F, board D at 4F, and board E at 5F. This slide gives an example of the tandem demodulation mode. Assume we have a magnetic field oscillating at 5 Hz with RMS amplitude B0 and a Hall effect sensor with a current passing through it, AC excited, 23 Hz and with an RMS value I0, then the current and the voltage can be measured with the 9210. The magnetic field is sinusoidal at 5 Hz and the current driving through the Hall sensor is at 23 Hz. The Hall voltage is the product of the Hall resistance, the magnetic field and the excitation current, which in turn can be shown to give rise to components at the sum of those two frequencies, 5 Hz and 23 Hz, and the difference of those two frequencies. The 9210 allows you to measure the current at the frequency of the Hall sensor, 23 Hz, and the Y component of the voltage present at the difference or sum frequencies, and using both those values it's now possible to calculate the Hall current and the magnetic field. It is possible to use both internally generated frequencies as well as those derived from the externally applied reference via the digital phase lock loop. The software can be used to perform frequency response measurements directly. A frequency sweeper menu can be used to define start and stop frequencies and perform linear or logarithmic sweeps between them, whilst the data plotter menu can be used to show the instrument outputs as the frequency sweep occurs. In the plot shown here we see the low-pass frequency response of the test network as measured earlier. The RJ45 connectors on the front of the Model 9210 are a new departure for us to use in making instrument signal connections, so for customers who would prefer BNC connectors, we offer the BB-BNC breakout box. Patch cables are connected between it and the 9210, and then flying leads internal to the BB-BNC are connected as required. The 6 RJ45 connectors on the front of the BB-BNC are wired to internal pin headers. Internal flying leads to the 24 front panel BNC connectors have 2-pin sockets fitted, which can be plugged onto the headers. So for example, you can use the box to connect 5 oscillator outputs, 10 signal inputs, and 1 external reference input in a 9210, which itself is fitted with 5 signal processing boards. The instrument specifications are given in the detailed datasheet, so I will not repeat them here. However, it is worth noting that the 3 different input modules which trade off input noise versus input impedance. The 9210's sensitivity is quoted as peak-to-peak rather than RMS, which is common in all our other instruments, because in the 9210 it can process more than just sine waves. The 1 megasample per second DAC means that the oscillator output waveforms above 100 kHz show some more distortion than would be the case, for example, on a Model 7270 or 7280, and that is what restricts the maximum recommended frequency range to about 100 kHz. How does the Model 9210 compare with the Model 7210? These 3 slides cover the differences in some detail. Firstly, both units can be supplied with different numbers of channels, but in the case of the 9210, these can be added by the customer after purchase. The 7210 requires factory installation and recalibration. However, the 7210 can support up to 32 measuring channels as opposed to the 9210's 10 channels. The inputs of the 7210 are single-ended voltage inputs with a relatively low input impedance, whereas the 9210 has true differential high impedance voltage inputs. On this slide we see that the 7210 has only AC coupled inputs, which makes it unsuitable for low frequency or DC work. It is also only an external reference unit. It has no built-in oscillators. However, in external reference mode, its analog phase lock loop will exhibit a lower phase noise than the digital PLL used in the Model 9210. The 9210's internal oscillator outputs include output current measurement. Finally, this third slide emphasizes the tandem demodulation mode available in the 7210. Tandem demodulation is also possible in the 9210, but the units must have at least 2 signal channel boards fitted. The slide also mentions the differences in the computer interfaces of the 2 instruments and the supporting software that is available for them. As I draw this presentation to a close, I'd like to emphasize that the 9210 is very much more than just another lock-in amplifier. Traditional lock-in amplifiers are seldom used alone, but in many cases the 9210 will be the only instrument that is needed for an experiment. Complex experiments can need multiple signal channels, and in the past that meant multiple instruments. The 9210 can eliminate that requirement. The 9210 allows recording of DC signals as well as lock-in detection. The MCL software makes it very easy to use, and the LabVIEW driver caters for those who want even more flexibility where they do wish to include it as part of an even larger system. And finally, it is a physically compact, robust and lightweight instrument.
Finally, I thought it would be useful to consider the typical applications for which the Model 9210 is ideally suited. AC impedance measurements at frequencies up to 100 to maybe 500 kHz, but especially in low temperature physics. AC calorimetry work, 3 omega thermal conductivity measurements, multi-channel optical measurements, multi-channel magnetic measurements, multi-channel vibration studies. But most importantly, just ask your local signal recovery distributor or sales agent, and he or she will be able to advise you further. Contact details for all our distributors can be found on our website.
Thank you for watching and listening to this presentation. Goodbye.